Hi everyone, can everyone hear me? Good. My name is Unna, and today I'm just going to talk to you about a few simple, accessible philosophies that you can use to write better factored Python code. Before we begin, a couple of things. First of all the code from this talk is available on GitHub. There is a shortened URL up there. It's more for future reference in case you want to look back at anything you see. So you don't have to follow through now, but it'll be there for future reference. Secondly, a bit about what I do. I'm a software engineer at Deloitte in our AI and analytics team. Deloitte's a fantastic place. We work with many of the UK's biggest companies. If you're interested in a career that's you're always working with a different tech stack, then please feel free to hit me up. My email address is handled up there, or of course you can just grab me outside. I'm here until Tuesday, so feel free to talk to me. So, to set the scene for this talk, imagine that you're building a tool using Python from the ground up, like from scratch. Now, initially you're going to start out with a couple of classes, functions, and modules. And even if your code's not that well set out, it's small enough that people are going to be able to follow their way around it. But as time goes by, the environment becomes more complex, you're adding more and more features, and after a while it feels like a bit of a mess. And apart from the fact that this just makes you feel less happy when you look back at what you created, there are some real tangible costs to this. First of all, it becomes really difficult to onboard new developers. People are going to spend a while just trying to work out how your code base works and how it fits together, which is time that they are not spending actually adding features, which is what they're there to do. It means that changes can have unpredictable side effects. Right? Somebody changes a function and it's not clear how that fits into the overall framework, and that can cause bugs. And then finally, it can just take longer to implement new features and do new things, because there's no clear framework how everything fits together, so it becomes more of a bespoke task to extend your product. So, what do we do about these problems? Well, as the talk's name suggests, we refactor. So refactoring is a really general term, and essentially all it means is that you change the code base without changing what it does. So if prior to a refactor, input X leads to output Y, post-refactor, input X should still lead to output Y. From the perspective of a consumer of your code or a client, nothing has changed, but internally we have somehow improved it. Typically this will refer to either it's more maintainable and easier to manage, or sometimes people use the term for making it more performant, but still kind of doing the same thing. We're going to focus on the former in this talk. It's more about kind of how to refactor your code to make it more maintainable, extensible, and so on. Now, refactoring is a really important topic in computer science, and a lot has been said and written about it. Up on the slide here are 3 classic works on the subject, and there's a whole load more material out there. And it's these, you should absolutely go out and read these books. They're super important. Refactoring is a super important skill set for a software engineer to have. And you're not going to get from this talk as much as all the information that's out there, so I highly recommend you go and read up on it. But the aim of this talk is more just to shortcut your learning by highlighting some of the most important ideas in this literature, and specifically to discuss how Python can help you realize these ideas in the most efficient way. So Python has an excellent standard library, it's got an excellent ecosystem of third-party modules, and it is just a high-level language in general. And so some of these ideas that are presented in these books, potentially in a Java or C++ environment, can be applied. You can kind of supercharge your approach using Python. So I hope you find it useful. I'm just going to jump right in. We're going to go through 3 kind of philosophies which you can apply. Keep the core logic obvious. I'm going to jump right into an example to show why I do this. Suppose that you've got, I hope this, I don't want to read this. Suppose you've got some code that's dealing with customers. And here we've got a customer, and we're just representing them using simple dictionary. And they've got a first name and a last name. And we want to write a function that's going to swap the first name and the last name. So right now, they're John Smith. We want to change the first name to be Smith and the last name to be John. Alright, so we've got a function that does that. It's called swap names, and it's going to take as the argument the customer. And the way it does it is it assigns their first name to a variable called temp, then it assigns their last name to their first name, and then it assigns the variable temp to their last name. Simple enough. Now, it turns out Python gives us a better way of doing this, and many of you may have seen this before. It's a fairly well-known trick, where we can just say customer first name, comma, customer last name equals customer last name, comma, customer first name. This is cool. If you haven't seen it before, then yeah, you can use it. Well, when I first saw this, I thought, yeah, this is great. This is a big improvement on what was on the previous slide. It's a little bit more difficult to articulate why, though. Like, it's not actually that much shorter. I mean, it's slightly shorter, but I don't think that's what we really like about it. And I think if you analyze it, what's really cool about this is that it says exactly what we want to do. Like, customer first name, customer last name equals customer last name, customer first name. It's kind of just saying swap first name and last name. What we had before was, it had the same high-level idea, like, but we had to create this temp variable, which didn't have any real external meaning. And then we sort of kind of roundabout way, by the third line, you can kind of see, yeah, we realized our original high-level idea of swapping the first name and the last name. But here, we just do it like directly. Now, if we suppose Python didn't have this kind of neat little trick, we could still adhere to this kind of philosophy of trying to like do exactly, like trying to not do things in a roundabout way, but do exactly what we want immediately by doing something along these lines. Here what we do is we define an auxiliary function called swapDictValues, which is going to take a dictionary and 2 keys from that dictionary, and it's going to do, using our temp method, because we're kind of assuming we don't have this, this neat bit of syntax, it's going to do that swap. And then in our swap names function, what we do is we call swapDictValues, and we pass in the relevant arguments. And in this way, like, if somebody looks at the swap names function, they can potentially see exactly what it's doing without having to delve into the nuts and bolts. So it's nice that we can pull out the low-level nuts and bolts from the high-level, like, business logic. So this is what I mean by keep the core logic obvious, right? You shouldn't be conflating nuts and bolts and like implementation with high-level logic. Another example along the same lines happens with error handling and logging, this kind of typical administration that goes alongside core business logic. In this bit of code, we've postulated the existence of a package called database, which is kind of made up, and it's giving us an API called getUserById. And the way getUserById works is we pass it, it's a function, we pass it a user ID, and it's going to return us some kind of object that represents a user. And if that user doesn't exist, then the database is going to raise an item not found error, right? So when we're using getUserById in production code, well, we might want to do a bit of logging, just about like, I'm trying to get this user ID from the database now, and we might do just a bit of error handling, so we want to catch the item not found error. We also want to catch maybe any other error, like maybe there's some kind of database connection error or whatever, and just handle those gracefully. So this bit of code does just that. The function getUserData is essentially a wrapper around getUserById. It does a bit of debugging and catches the errors and does some, when I say it does a bit of logging, and then when it catches an error, it logs what's happened. And you can imagine putting more logic in that. Now this is fine, it works, but there are 2 problems. The first is this is just a bit difficult to read. Like this getUserData function isn't really doing anything. Like it's just a wrapper around another function. In most normal circumstances, we don't care about, if things are all working, we're not going to read the logs anyway. And so, so it's a bit difficult to read, even though it does what we want it to do. And secondly, suppose like the database gave us a getUserByName function, we'd probably just repeat this logic more or less. So but as it is here, we can't like repeat all that error handling and logging in an easy way. A great way to get around this is by using a context manager. If we use a context manager, I'm going to kind of show you, first of all, what the context manager looks like. So what we do is we have, we do from context lib import context manager, and we essentially have this function dblogger, and it's going to do all this, it's going to look just the same as our previous function, except from instead of doing the business logic, it's just going to have like a yield keyword in place of that. So it's really just a copy, but we just yield instead of doing the business logic. The way we use it is like this. We have a with dblogger, and we pass it the appropriate arguments. And then inside that with statement, we just put our business logic. And at execution time, what's going to happen is where that yield statement was, is going to execute what was inside our with statement. So in this way, we've managed to pull out all of our logging and error handling into a separate unit. And when somebody looks at this function, get user data, they can just see exactly what you're trying to do. I think this is great. Like, if somebody's looking at this, if somebody's reading this get user data function, then they can just immediately see, okay, like, this is just calling get user by ID. Now, if I'm really interested, I can have a look at your DB logger and see how it works. But if I'm not that interested, like, maybe that's enough information for me already. So it makes it far more readable to just kind of follow what's going on for a reader. From the point of view of the writer, it's pretty much like the same kind of work, but it just makes it more readable. So to summarize this first idea, it's easy for complexity to creep into your code by mixing up either like low-level mechanics or administration logic with core business logic. You need to remain vigilant to that and factor it out. It can happen quite subtly, so it's something to kind of always be aware of, like, is this function really like doing one thing, like just kind of like implementing something in a really clear way, or have I mixed up a little bit of admin or lower-level mechanics with my high-level ideas? The second of our kind of philosophies is use the right data type. Again, I want to jump right into an example to demonstrate what is meant by this. Suppose we're back in the situation where we've got a swap names function. But this time, we just want to do a little bit of kind of verification on that user, on that customer object, before we swap the first name and the last name. All right? So the function looks the same as it did before, except when we have if first name not in customer or last name not in customer, return false to indicate a failure. And then we do our swap, and finally we return true to indicate a success. So that's fine, this is a pretty normal thing to do, right? You like return false for a failure or true for a success. And it's fine and it works, but the problem with it is, if this is in a large code base, the word false doesn't actually mean a failure. And somebody who's calling this function will need to know that when it returns false, it means failure. Right? So the word false in the English language and in computer science is not synonymous with failure, nor is true synonymous with success. So that is a piece of specialized, like, function-specific knowledge, like implementation-specific knowledge that the caller would need to know. And in a large code base, or even in a medium-sized code base, this could begin to get confusing. A nice way that we can solve this problem is by using an enumeration. To do this, we just do from enum with a lowercase e, import enum with an uppercase e, and we create an enumeration called status by doing class status inherits from enum. We give it two attributes, which conventionally we'll write in uppercase, success equals 1, failure equals 2. The values are not important as long as they're distinct. And then the rest of our code is the same, except when we just return status.failure when there is a failure and status.success when there's a success. So now, when the caller receives the response, they receive an object. They don't just kind of receive a Boolean, which is a more high-level data type, which you're kind of overloading for a specific purpose, but they receive something which says exactly what it is that you mean, a data type which is specific for the exact purpose you're using it for. A slightly more broad example of this comes when you're using SQL. This bit of code here is going to get someone's nickname from some kind of SQL
database. And the way it's going to do it is it's going to construct a SQL query as a string.
So what it's doing is it says, def get nickname, user ID is the argument, and then it's going to create this string called SQL, and it's going to say select username from users where user ID is equal to the supplied user ID. All right, so this is cool. We're assuming user ID is an integer here, and so if it's an integer, then this is going to be valid SQL, and we can then send it to a SQL server. But again, kind of in a similar way to before, we're overloading the string data type to represent some SQL. Sure, you can represent any SQL as a string, but a string is a more general thing than SQL. And we have not in the standard library, but as a third-party module, we have SQL Alchemy Query Builder available, which will provide us with a specialized piece of machinery for building a SQL query. This works by, we first of all need to define our users table. So we say users equals SQLAlchemy.table, and we just need to tell that API the name of the table, the metadata, and some column names. And then we define our SQL statement in terms of that table. So I'm not going to go through the API in detail, but essentially we do SQL alchemy.sql.select, we tell it what we're selecting, .where, and then we tell it what the condition is. Now, unlike in the previous example, like here, we have lost something. It's not quite as readable. I mean, most of us who use SQL are probably like primarily comfortable with just like raw SQL, and it's not many people would say I'm more comfortable using like the SQL Alchemy API than I am just writing raw SQL. Sure, that's a valid criticism, but you need to also be aware of what you gain by doing it this way. First of all, this is now portable across different SQL servers. So whereas if you were writing a string, you would need to consider the dialect of the SQL server, here you know that your code can execute on MySQL, Postgres, or NSSQL, or whatever it is. Secondly, it means that the error checking, if you make a syntax error, like if you make a syntax error in your Python, then your Python just won't execute. It won't try and send something erroneous to the SQL server. Whereas here, although you can make a logical error in how you construct your SQL, you know that at least SQL Alchemy is going to send a valid SQL query to the server. So you're going to catch errors earlier. And finally, you might have noticed that here we're a bit vulnerable, potentially, depending on how the rest of our code looks, we're a bit vulnerable to a SQL injection attack. So, craftily formed user ID could leave us vulnerable to having people execute arbitrary code, whereas here, that is going to be taken care of by the package that we're using. A final example in this category is name tuples. Suppose we've got a function here, getLatLong. So this is doing a reverse geocode. We're taking the city name, the name of some city as a string, and we're going to do something, and we're going to return the city's latitude and longitude. So that's fine, and we're returning it as a tuple, where the first element is the latitude, or the 0 index is the latitude, and the 1 index is the longitude. So when we use the return value from this function, we have to remember that the 0 element is the latitude, and the 1 element is the longitude. Again, the caller needs to know kind of specific information in order to use this function. A better way of doing it is we can use a name tuple. We do that by doing from collections import name tuple, and then we create something lat_long pair, which is a name tuple. We need to tell the name tuple the name of our name tuple and the fields that it has, lat and long. The rest of our code is the same, except from instead of returning just lat_long as a tuple, we return lat_long pair, and the arguments to that are going to be the lat and the long. And when we then use that return value, we can take the return value .lat to get the latitude and the return value .long to get the longitude, rather than remembering that the 0 index is the latitude and the 1 index is the longitude. So again, it's not a transformation, it's not completely changed the way our code works, but it's just made it that much easier for the caller to use without having to remember specific details about every bit of our code. So to summarize the second philosophy that we have, if you use a general purpose, overload, if you will, a general purpose data type to represent a highly specialized idea, it can lead to poor readability, a lack of automatic validity checking, and a lack of portability. And the great thing is that a lot of the tools that you require to use specialized data types are right there in the Python standard library or as well-maintained third-party modules. So there's really no reason not to take advantage of that. The final philosophy that I wanted to talk about is called code as a liability. This is an idea which is inspired by a talk from PyCon US 2012 by Jack Diedrich, and it's entitled Stop Writing Classes. It's quite well known, some of you may have seen it before, and I highly recommend you go and watch the full thing, it's really good. But what follows are a couple of kind of key ideas that I've taken out of that talk. Preferred built-in exceptions. So what we have here is a function called getUser, and it's going to take a user ID and it's going to try and get some information about that user. If the user's not found, it's going to raise a user not found exception, which is a custom exception that we've created. A really kind of simple way of just making this a little easier for everybody is to not use a custom exception. Here we are raising a value error instead, and the problem that we've got here is that the user ID isn't recognized, so a value error kind of semantically describes what we're doing anyway. One of the big really practical problems with using the kind of custom exception is that they're often defined in separate modules. So you might have an exceptions.py in your package, and that exceptions.py is like, if somebody sees the user not found error, they have to like dig into a different file to see what's going on and what it does. So unless you've got a really good reason, just raise one of the built-in error types. They cover most scenarios which could ever go wrong. A slightly kind of broader thing, because I mean, obviously an exception is kind of a type of class, but in general, challenge yourself whenever you're creating a class to, like, as to whether you need it or not. Just here we've got a fairly, well, this is actually something I came across like in the wild. This is something which I actually used in some code or saw somebody else using. We've got a class to represent a time duration. What it's going to do is it's got a start time attribute and an end time attribute, and it's going to store those two attributes. And then it's got one function or one method called getSeconds, and it's going to get the total number of seconds between that start time and that end time. This is fine, and in a way, it's like this is a typical time for using classes, right? You've got two pieces of data, and you've got a method which is defined on those data. So like this is a textbook example of when you would want a class. However, you could also do this. You can create a named tuple called time duration, which has a start time and an end time attribute. And then you can create a function called getSeconds, which acts on one of your time duration named tuples. I would argue that this is more simple to read. It's just defined like two things, one data structure, and then one function on that data structure. Now, you can't always reduce classes down to this. If you're using, say, overloading, then you need classes. And if you're using a complex inheritance structure or hierarchy, then again, classes are going to be necessary. But in many events, it turns out like classes are not necessary, and you should, again, be kind of aware of that, like, and be aware when you are using a class, make sure there's a good reason for it. Finally, again, kind of along similar lines, in Python, modules are only required for namespacing purposes. This means that if you say got three utility functions that you just feel like are general utilities, and three database functions which are going to talk to your database, there is no need to create a separate utils.py and database.py file for each of those sets of functions. Because with 6 functions in total, you can perfectly well manage 6 names in one module. And that is the only real reason, I've ever been aware of for creating modules in Python. To give an example of how far you can take this, if you so wish, PyParsing is a package which can parse arbitrary code, so you tell it the syntax and it will do the parsing for you. So that's a super complicated thing, right? And the whole thing is just implemented in one module, which is 6,700 lines long. Now this is probably taking it too far. Like, they do actually probably have names, but it does say in their contributing.md file that they do have namespacing problems. So this is probably going too far. I don't recommend you go this far, but it does show that like there is no necessity. Nothing's forcing you to create modules. The only reason why you need to create them is to manage your namespacing. I think like there's a common thing in this last section, which is you should ask yourself when you're doing something because you think it's a best practice, you should challenge yourself as to why that best practice exists. Often best practices, often the things that we've talked about in this section are done because other people do them and because people are used to doing them. For example, in Java, you need to create classes because that's how Java works, and classes more or less need to be one class per file. But that's just like not relevant in Python. And in C and C++, you can use different files for implementation hiding. Again, not relevant in Python. So just make sure, like, when you are writing extra lines of code, you're aware, okay, this is like more code that I've written now. Somebody has got to read more lines of code and maintain more code, and that's going to confuse someone in the future. Is there actually a good reason for doing it? Or, like, have I just done it because that's what I do? So to sum up, our 3 ideas. Keep the core logic obvious. You can make functions, context managers, whatever you need as necessary to achieve this, and pull out administration and low-level details from your core business logic. Use the right data type. So take advantage of all the stuff in the standard library and third-party modules as necessary to use specialized tools for whatever tasks you have. And code is a liability. You should challenge yourself to write as little of it as possible. That's all I have. Thank you very much.
Okay, thank you to Jacob. He's going to take a few questions. We've got about 5 minutes, so maybe one question. Please stand up and enunciate, because I do not have a handheld microphone with me. Any questions? No? One question. Go for it.
When is that point when you should think about refactoring your code? Right, where's this trigger? Like, you see the code, and should I do that? Should I not?
Yeah, I mean, I think that's it's more of like a management question as anything. I think that the ideal is that you do it on an ongoing basis. I think like some of these ideas that we've talked about today are ideas that you can just apply on an ongoing basis. It's like just keeping your code well factored as you write it. That's kind of the angle that I was coming at. But I think that obviously there will be times when you do need to kind of take a step back and refactor. I think like as much as possible is probably the answer, like in an ideal world. I don't think that, I mean, obviously there's practical considerations in any project, so I think that'll be what drives it, as opposed to any kind of theoretical answer to like the optimal level of refactoring.
Okay, I think that's all we've got time for. Thank you very much, Jacob.